come to you as an email, you have to send to others, giving access to whole batch 2102 @ Kolkata.
Yes, sir.
After the class. After the
Yes,
class.
sir.
Okay.
Sangeeta, did you understand?
Yes, I understood. I tried it out yesterday, so it is fine. You do get the link, but it takes some time.
You have to give access to this video. Then they can download it from the Google Drive.
Yeah, I will put up the link on WeLearn after the class. Once it is processed, it takes some time, I noticed, for the link to come. And after it comes, I will post it on WeLearn. Okay?
Right.
Yes. So, hello everybody again. I am sure some people will come and go as we proceed with the class, but I hope you don't get disturbed by it. So first and foremost, I would have liked to see all your faces, but I think it is a bad idea at the moment. I will see you when we meet in person sometime. As I gather, some of you have already attended a quantum chemistry course by Professor Pal last semester, but this is a subset, so I will just assume that we are starting from scratch, and we will move from classical to quantum, and then learn more about how quantum mechanics and quantum chemistry is affecting life today. It is now everywhere, so it's not something that you can miss. Even a lay person has heard of quantum, even if they do not know what it is. So I will now start with my presentation, and the way this will go is I will I will do an overview presentation, and I will do the details that you don't find in notes and books or even online. But what I found was that internet resources for the general concept is very, very good. So they show well, is there a problem with hearing me?
No, I'm able to hear.
Okay.
It's okay.
Someone messaged saying they cannot hear. Okay. Anyway, so fine. So the way what I have thought is, since everything we're doing is now online, so it's best to make use of the good resources that we have online. What I will do is I will provide the links and the background and why people did what they did. And then I will skip to doing the details of the derivations and the mathematics, the steps that are not always available. And for in between concepts or, advantages, disadvantages, and the general thing, I will touch upon it. But I will give you links to internet resources where really they do a very, very good job. I am not able to make animations or demonstrate it as well as they do. So I will give you links to those things and you can watch them. Those are basically one-time watches, or maybe 2 or 3 maximum. It's not like you have to learn them up or use them as material for your exam. So the notes I provide as notes, those will be relevant for your exams and learning, so to speak. The internet resources are just for concept. Okay. So with that, I will start presenting. Yes. So I hope you can see my presentation now. So this is the presentation that I have uploaded on WeLearn as well. So this file will contain lectures 1 to 5. 1 to 3 is already available. And I will replace this file with something that has all 5 lectures after the 3rd lecture is done. Okay, so then you will have all 5 lectures in one PDF file. So during the first module of this course, that is the first 5 lectures, we will cover 5 topics. We will compare classical and quantum mechanics, which we do today. Then we will go through the major failures of classical mechanics. These are mainly phenomena which classical mechanics was not able to explain. Then we will talk about wave-particle duality, what it means, its implications. Then the Heisenberg uncertainty principle, and finally the quantization of both energy and other quantities like momentum and angular momentum. Now, as I envisage, the goals of this course will be to know what is quantum mechanics, why it was needed in the first place, what it could do before, what it can do now, and also what can you do with it. So where is it going at the moment? And in the process, quantum mechanics provides a very good example of how science progresses. So in the process, we will learn how to explain an experimental observation. So the first step, of course, is always to apply existing knowledge to see if it can explain what I am seeing. But often this proves to be insufficient, and then you have to develop new concepts. And in both cases, you have to be able to work out the math, to use the existing knowledge to explain the observation. And this linking might seem very, very difficult in many cases. And then when you do the math, you also sometimes discover other interesting implications which help you to frame more experiments to make sure that your theory is correct. Now, the first part of being able to apply existing knowledge is a skill that every scientist must acquire in the course of his or her training. The developing of new concepts is much more challenging, and although it would be nice if all of us were able to do it, but it really is a very rare skill to be able to develop new concepts to explain an observation. And doing the math is, of course, the other skill. So you must know what knowledge can be applied to explain your observation, and you must be able to apply it by doing the math. And we shall see how this applied to quantum mechanics as it progressed through over about 200 years. Now, of course, we have all grown up with classical mechanics, the Newton's laws, and the laws have always been predicted. So we were always told that this car is moving at such and such speed and is at such and such position, and where will it be in 5 seconds, or how far will it have gone in 20 seconds. So this was how you always thought about mechanics, that knowing the current situation, you are able to predict the future. But this Newtonian mechanics fails in 2 domains. One is at very high speed, so when it is close to the speed of light, and then you need to apply relativistic corrections to these Newtonian equations. And the other domain where it fails is a small size, when things are very, very small. And then the so-called quantum effects come into play. Sadly, just a quantum correction is not available. What happens is the full picture of how to think about the system changes. And when classical mechanics is challenged and there is high speed and small size, then the line between matter and radiation becomes blurred. So there is E is equal to mc squared, which means that energy and mass are interconvertible. And then there is the quantum effects where you have wave-particle duality. So there is matter waves, for example. And then what is wave or what is matter and what is energy, everything becomes blurred. And you will see that sometimes even after quantum and relativity, there is also quantum electrodynamics, and that is another ballgame altogether. So things get more and more complicated. And why is it called mechanics? You will see that mechanics, as you know it, it's not very apparent when you look at quantum equations. But why is it called mechanics? It is called mechanics because there are two clear aspects of it. There is statics and there is dynamics. So there is a part which is time independent, and in the so-called equilibrium systems in classical terms, and there is dynamics, which is the progress of the system with time. So what is special in quantum mechanics? In quantum mechanics, the momentum is not a function of mass in general. It is related directly to the wave nature of the particle or light or whatever. It is related to the wavelength of light, of the wavelength of the wave of the particle. Now you might say, but to determine this wavelength, we use mass into velocity as momentum. Then how is it not a function of mass? The way you can think about this is that when quantum mechanics does not distinguish the particle from a wave, and you represent everything as a wave function, then the more fundamental quantity is the wavelength. For particles, so if it's an electron wave, then it so happens that the wavelength is determined by the mass and the velocity for an electron in motion. But for light, for example, the wavelength is the intrinsic property. So what quantum mechanics says is that momentum and wavelength, these are more fundamental quantities than mass and velocity. Okay. Then the second most fundamental point is what names quantum mechanics quantum. That is the quantization of energy and momentum. So the spectrum of energy and momentum are discrete. So they're like steps rather than a slope. And this is what led to the inception of quantum mechanics in the first place. The fact that not all energies are possible for a system. It has certain allowed energy levels. The third thing is that quantum mechanical equations are different from Newton's equations in being probabilistic. They are not deterministic as Newton's equations. So the quantum equations do predict the future. They do predict the future state of the system, but in a probabilistic fashion. So given one system, you cannot say what it will look like in 10 seconds. But given a large number of identical systems, you can predict the distribution of states of the system after 10 seconds, of all the systems, provided you have enough number of identical systems. Then the fourth thing is that particle trajectories are obsolete concepts in quantum mechanics. So given an electron, if you ask quantum mechanics to tell you how this electron will move around in 2 seconds and trace its path, it is unable to do so. Again, this is related to the probabilistic picture that quantum mechanics presents. Here, only the ensemble picture or the probability picture is relevant. You cannot talk about the path of a particle. Then comes the last point here. Of course, this is not an exhaustive list, so I'm just trying to highlight some important points here. the last point is related to the Heisenberg's uncertainty principle, which is that if you probe a quantum system to find out what state it is in, it will collapse into one of a known set of states. This set of states is a characteristic of that system. They are the eigenstates. And it will collapse into one of them. But you cannot know which one. So again, if you have a set of identical systems and you probe them all together with the same radiation, or however you want to look at it, each one might collapse into a different state, or some into one and others into another, and you will get a probability of obtaining these eigenstates. So what you can conclude from such an experiment would be that the system was originally in what is called a superposition of states. So it was simultaneously in many, many states, which each had components of the eigenstates, which are characteristic of the system. And when you probe it, it falls into one of them randomly. This is something that is very bizarre to most people. And it is something that takes, I think you never really understand it entirely. But that is how the system works. And once you know the rules of how it works, you have to work with them, I think.
Ma'am?
Yeah?
I had a question. How do you probe a quantum system?
Oh, by probing, I mean, if you want to look at it, so you would normally shine light on it. So it's just like, how do you, even classically, when you want to see where something is, you look at it, which means you collect the photons that reflect off it. So it's the same with the quantum system, that you throw a proton at it and see from where it reflects, or if it gets absorbed or something. It's normally the photons which are used as probes.
Oh, all right. Thank you.
Yeah. Okay. Okay, and at the bottom of the slide now you see something called the Burial Theorem. Now, this is something that carries through from classical to quantum mechanics. So this is tremendously useful. It's a theorem which, well, what I have written on the slide is not the exact statement. The exact statement is mathematical, and if we have time, I will go through it. But the Burial Theorem basically states that the ratio of the average kinetic energy and the average potential energy is a constant characteristic of the system in most cases. This is a theorem from classical mechanics, but this was found to hold even in quantum mechanics. And it is a very powerful theorem and is used to derive many results. I will probably have one assignment on the Burial Theorem when you will understand it better. Otherwise, we can have, after I finish this module, we will talk about the Burial Theorem because it's very, very interesting.
Yeah, Sangeeta, anyway, I will be covering it in the quantum mechanics.
Oh, okay, okay. Then that's fine.
When I start the postulates of quantum mechanics, etc., Burial, Ehrenfest theorem, they will all come.
Ehrenfest. Okay, okay. Then that's fine. Then Professor Pal will take up the Burial Theorem. But the interesting thing that I wanted to point out was this was discovered in classical mechanics and it carried through to quantum mechanics. Although there was no reason for it to do so, but it did. Okay. And then the rest of the class today is basically a story, the story of quantum physics or chemistry. And what I wanted to show you was how long and how much effort went into developing this and how far quantum physics and chemistry has come. So, and if you see the first date here, it's 1814. That's more than 200 years ago. So the story starts very, very long ago. And from something very simple, from the solar spectrum. So Fraunhofer, who was a lens maker, he found that in the solar spectrum, there were some dark lines, and he could not explain this. So there were these lines in the continuous spectrum which indicated that these frequencies were missing somehow. But what was the reason that they were missing? He documented 6,000 such lines, almost around 6,000. But he also surmised that perhaps these are the frequencies which are absorbed by substances in the atmosphere. But that was conjecture, and he did not really know what was happening. But this was the first indication of quantization of energy. So the elements like oxygen, nitrogen, etc., these were absorbing some specific frequencies from sunlight, resulting in these dark lines. Then in 1819, in a completely different field, Dulong and Petit, they were measuring the specific heat capacity of atomic solids. And they found that that all these atomic solids, they had a constant molar specific heat capacity. But this was only at high temperature. As you moved to, if you did the experiment at low temperatures, then this value of heat capacity was no longer constant. It was found to be proportional to T cubed, to the cube of the temperature. And they could not explain this. So they formulated a law for the high temperature behavior, but the low temperature remained unexplained. In 1859, along the lines, Kirchhoff started thinking along the lines Fraunhofer was thinking, and he proposed that the line spectrum, both absorption and emission spectrum of substances, were fingerprints of substances, and they could be used to identify the substance. So this was immediately picked up, and people started using this as an analytic tool, but no one really knew why they are fingerprints and why only specific frequencies are absorbed or emitted. Then 1 year later, Kirchhoff wanted to record a black body spectrum, the so-called black body spectrum. So this is so a black body, he defined it as something that can absorb and emit all radiation, so all frequencies. The most well-known black body at the time was the sun, which was thought to emit all frequencies. But the solar spectrum, since it is a complicated phenomena coming through the atmosphere, and really it's not clean, so to speak. So Kirchhoff designed a black body in the laboratory, which could absorb and emit all frequencies of radiation, and then he recorded the black body spectrum. And then from 1860, for the next 40 years, people tried and tried to explain the nature of the spectrum. So in and then finally in 1900, Planck managed to derive the law which fit the full spectrum, but we will come to that later in much more detail. Then in 1885, the hydrogen atomic spectra was recorded, and the Balmer series, which is in the visible range for hydrogen, this could be fit to a certain formula, the Balmer formula. And 3 years later, Rydberg extended this formula for all the series of lines in hydrogen. So in the UV range, the IR range, the visible range, all the ranges, he found a common formula. But these were all empirical formulas. So they looked at the spectrum and found that this fitted, that this formula fitted. There was no derivation for this. Then in 1887, the famous photoelectric effect was observed by Hertz. Now, a common misconception is that the photoelectric effect, when it was studied in great detail the first time it was observed by measuring the kinetic energy of emitted electrons, etc., as we are taught in school. That you shine light on a metal and then the electron is emitted, and the kinetic energy of the electron is measured by stopping it with an electric potential. But Hertz did no such thing. What Hertz observed was that a negatively charged body gets discharged more easily if you shine UV light on it. So it was really a very, very simple observation, but it was not explainable. And this was the first photoelectric effect. Much later, it was studied in more detail before the explanation, theoretical explanation was attempted. We will see when it was done. It's, I forgot the date. It's a little bit later. Yeah, that's in 1902. Okay. Then in between, there was the discovery of X-rays. Then there was the discovery of the Zeeman effect. Now, the splitting of spectral lines under magnetic fields, this is a very, very quantum effect. And the explanation came many, many years later, but it was one of the first things that was observed, even before the name quantum came into existence, quantum phenomena. So the Zeeman's effect was discovered in 1896. Then in 1900, this is the year most people say is the birth of quantum chemistry, quantum mechanics. 1900, when Planck discovered that a constant called H could be invoked to explain this black body spectrum that Kirchhoff had recorded in 1860. So 40 years later. Okay. But his idea was, but he basically made only a small change in the classical attempts at explaining it. He just introduced a small idea that instead of allowing all possible energies, you only allow the radiating molecules in the black body to have specific energy levels in multiples of H. He just changed this part, and the rest of the derivation followed that of Rayleigh and Jeans. We will do this in the next class. We will look at their derivation and see how small the change Planck made. But it opened up the full field of quantum physics. Then in 1902, Leonard was the one who actually performed the photoelectric effect experiment that we always read about, where the kinetic energy of emitted electrons is measured. Okay, and in order to explain this, Einstein proposed in 1905 that just like Planck had proposed quantization of atomic energies or molecular energies, perhaps even the energy of light is quantized. Now, this was a very radical statement at the time, and it invoked a lot of criticism from eminent physicists. In fact, Planck himself said that in a recommendation letter for Einstein, that he may sometimes have missed the target in his speculations, as for example in his hypothesis of light quanta. This cannot really be held too much against him, for it is not possible to introduce really new ideas even in the most exact sciences without sometimes taking a risk. So Planck, who himself had proposed quantization of energy, did not believe that the energy of light was quantized as Einstein had proposed. But in 1907, Einstein went even a step further and used the concept of quantization to explain the low temperature behavior of the specific heat of atomic solids. Now, this was one more development in favor of the quantum theory, but there were still many, many dissenters everywhere. Quantum physics followed closely the development of atomic structure, theories for atomic structure. In 1909, we find Rutherford, Geiger, and Marston do the gold foil experiment, and which is the famous experiment that we have all read about. And they proposed the Rutherford model for the atom with the small nucleus and electrons revolving around it. And in 1911, Mulliken set out to disprove the quantization of energy by doing the oil drop experiment. But in the process, he found the charge of the electron and also proved the quantization, the concept of quantization. And he even got the Nobel Prize for it, in spite of not believing in the quantization in the first place. So, yeah, so it was lucky that Mulliken published even what he considered a negative result of his experiment. Then in 1912, Planck again used his own concepts to propose the 0-point energy. This is also very radical. So, so this was also and also encountered a lot of criticism from his peers, and he himself did not believe it actually. But in 1913, Bohr proposed his own model of atom by combining.
Excuse me, ma'am.
Yeah.
What is 0-point energy?
So the 0-point energy is that even at 0 Kelvin, if you have a, let's say, a vibrating object, you cannot reduce its energy to 0. So even at 0 Kelvin, it will have this minimum energy. I think in the during this course we will study a lot about it when we do harmonic oscillators and other things.
All right.
So there is minimum energy that you cannot take out of a system. Okay. Then in 1913, there was the Bohr model of the atom. And he basically combined the concept of quantization of atomic energy and the quantization of light energy to propose that for an electron to jump from one energy level to another, you need a certain fixed amount of energy. And this was also a postulate. So no one has really given an explanation. These are all phenomenological suggestions. Okay. Then, so these are all happening simultaneously. So there is the quantization of light, there's the quantization of atomic energy, there is the development of atomic structure, and there's explanation of very old experiments by using these new concepts. But there is no theory that explains everything yet. Okay. Then in 1913, Stark and Sourdough, they observed that spectral lines split also under electric fields. So normally when you study these effects, you would think that, okay, the splitting under electric field was developed first because that's how you study it, but that's not true. There was a very, very, almost a 20-year gap between the two. But the explanation of both lies in quantum theory. Then in 1914, Frank and Hertz performed another experiment, which is almost like which is also photoelectric effect experiment, but in a slightly different way. They measured the current generated by the electrons, and in several ways. So, after we do the black body radiation, when we do photoelectric effect, I will also go through the Frank-Hertz experiment. So it's a variation of the photoelectric effect experiment. And all this while, the argument between whether light is quantized or not, whether there are photons or not, this has been going on. Then in 1916, Einstein went a step further. He suggested that not only was the energy of light quantized, the momentum of light was also quantized. Okay? And this was related to the frequency. in the same year, Sommerfeld and Bohr modified their atomic model from circular orbits to elliptic orbits to explain the Zeeman effect. And they also suggested a sort of quantization of angular momentum of atoms, which can be called either semi-classical or old quantum chemistry. So it's not quite how we do it today, but it was a step in the right direction. And then in 1920, Bohr, Sommerfeld, and Wilson all together compiled their rules into what is called the old quantum mechanics quantization rules. And this involves quantization of both momentum and energy. Yeah?
Excuse me, ma'am.
Yeah.
How did elliptical electronic orbits explain the Zeeman effect?
Okay. So when you have elliptical electronic orbits, then you can have alternative orientations of these orbits with respect to the magnetic field. So depending on which, let me see how to put it. I don't think I can explain it to you verbally very well. I can write it and send you a note. Okay. I'm not sure how to explain it verbally. But if you allow elliptical orbits, their orientations relative to the external magnetic field give you two possible energy levels. So it's. I think I will write it down for you. Okay. Oh, I did not notice your name. Can you just tell me your name? Oh, Yusuf. Okay. Okay. Thank you. Then. Okay. Now, after this, in 1922, Compton made a very interesting observation. That whether by design or by accident, he was using very high energy radiation. He was using X-rays, and he was scattering them off free electrons. So this combination of very high energy radiation and very small particle helped him observe that the scattering cannot be explained unless you assume that the electrons also have wave character. So this is called the Compton effect, and he also provided the theory by which involved quantization of and relativity, quantization of energy as well as relativity, and further strengthened the fact that quantum physics was true and you could not ignore it, because there was a whole group of scientists at the time saying that you are just that okay, maybe this concept of quantization explains these results, but there is a better way of doing it. We just haven't found it yet, a more classical way of doing it, rather than claiming that energies cannot have continuous distributions. Then, in the same year, there was the famous Stern-Gerlach experiment with silver atoms, where they split when passed through a non-homogeneous magnetic field, and this led to the concept of quantization of angular momentum. So there were clearly two types of silver atoms and not a distribution. We will also study this experiment in detail, so it's okay if you don't understand it now, it's fine. Okay. And then in 1923, came the famous de Broglie equation, where he proposed that the momentum of all matter is quantized. So Einstein had only proposed that the momentum of light was quantized. But in 1923, de Broglie proposed that momentum of matter also was quantized and put matter and waves on the same footing. And this is what came to be called wave-particle duality. And then there was a whole, and then in the next 5 to 6 years, there was a huge explosion in the field of quantum physics. So in 1924, Shatyendranath Bose, he proposed the statistics which derived the Planck's laws, and this statistics also predicted the Bose-Einstein condensate. And a quest started to get it experimentally for many, many years, and eventually we did get it. That it started in 1924. And then in 1925, that's when the first proper quantum theory was proposed by Heisenberg. But he couched his theory in matrix mechanics, which proved very difficult for most people to understand, and it really never became popular. Then in the same year, Uhlenbeck and Hutschmidt postulated the existence of electron spin. So this was still theory. There was nothing that showed that electron has spin. They just suggested that the electron must possess a property like spin.
Excuse me, ma'am.
Yeah.
The Stern-Gerlach, as far as I know, the Stern-Gerlach experiment is a proof of the spin of electron. Like there is a.
So yes, it is a proof of the. But when they did the experiment, there was no concept of spin. So after the experiment, people started thinking about what could be the explanation, and it was proposed that the electron might have something like electron spin, which would explain the experiment. But the existence of electron spin coming out as a conclusion from a theory, that did not happen till Dirac formulated relativistic quantum mechanics. So this was more like so the experiment came much before. So it was not like Stern-Gerlach set out to prove the existence of spin by doing this experiment.
All right.
Yeah. It was like this. Okay.
Ma'am, what is the spin of an electron? Is it the like the rotation of Earth like things or anything other?
That is the classical model of electron spin. So if you want to think about it classically, that is how you would think that but it's actually just an intrinsic value, just like electron has charge, electron has spin. And this spin has properties like angular momentum. So the spin itself is not, it's not like the electron spins around its own axis. It does not. But it has a property which behaves as if it was spinning.
Okay.
Yeah. Then what we will study mostly is Schrodinger's wave mechanics for quantum theory. This was developed in 1926. So he developed his theory independent of Heisenberg, but later he showed, but in trying to show that his theory was different from Heisenberg, he ended up showing that they were equivalent. But Schrodinger's theory was more physically appealing because it dealt with wave functions, and people were more comfortable with electrons moving as waves than as electrons being matrices. So this was Schrodinger. And Heisenberg and Schrodinger had a lot of arguments over which one was better. Heisenberg was convinced that although Schrodinger claimed that his theory was physical, it was not physical at all. Because really, quantum mechanics is not physical. I mean, even today, even when you think of wave functions, okay, they may sound familiar after you've been with them for a long time, but actually they are very strange beasts. Then, continuing with the work on spin, Pauli proposed his Pauli exclusion principle in 1926, and then in the same year, the Stark effect was explained, and then the mathematical foundations of quantum mechanics was also laid. Now, this was a very, very important development. People many times skip this as a historical event, but this is a very important event, because without developing the mathematics of quantum mechanics, you could not work out a thing. Because really everything in quantum mechanics is hidden in equations. Just thinking about it does not give you any idea whatsoever. You have to understand what the equations tell you. And to do this, you needed the mathematics. So Neumann defined the operator formulation of quantum mechanics, the mathematical spaces in which to describe these wave functions, and he basically facilitated further development. Then in 1927, Heisenberg again created a lot of controversy by proposing the uncertainty principle. And this really
Ma'am, you are not audible.
I am not audible. Can you hear me now?
Yes, ma'am.
Yeah, oh, sorry. Okay. So then, yeah, so after Heisenberg proposed the uncertainty principle, everything went haywire again, and people started arguing. And in 1927, finally, there was the Solvay conference, a very, very famous conference, where 19 of the 27 attendees were Nobel Prize winners. And they had a very, very intense sessions trying to understand what quantum mechanics meant. Like what they could see that it explained things, but it was so difficult to understand what the wave function was and why there was an uncertainty and what exactly was happening there. It was at this famous conference that Bohr and Heisenberg finally settled on what we now teach everybody, that that wave functions are basically a probabilistic picture of the quantum system. And you just have to think of it as a probabilistic picture. But many people at the time did not accept this. Okay? Then in 1927, the wave nature of electrons was proved by the Davidson-Germer experiment. We will also study this experiment. So the photoelectric effect taught us the particle nature of light, and then the Davidson-Germer experiment taught us the wave nature of electrons by showing that they diffracted. Okay? This is a picture of the Solvay conference. And when you have time, you can look at it and try to identify all the famous scientists that you know. So there is Heisenberg, Schrodinger, Einstein, Lorentz, lots of famous people, Marie Curie, everyone is there. And this, the picture on the right, that is Bohr and Einstein, where they had very, very strong arguments about why quantum mechanics is or is not true. Okay, and on the left there is Pauli, Bohr, and Heisenberg. Then in 1927 there was a relativistic picture of the electron that was proposed by Dirac, and he showed that his equation naturally indicated the presence of electron spin, but it also created many more questions. we will not, I don't think in the course you will come study relativistic quantum physics or quantum chemistry, but that is even more unbelievable than the non-relativistic one. And since quantum equations are so complicated, Dirac proposed the equation, but he only solved it for a free electron. And then in two other people, Darwin and Gordon, they solved it for a bound electron in a Coulomb potential. So if you have a hydrogen atom, for example.
Excuse me, ma'am.
Yeah.
Actually, I could not get the concept behind the spin of an electron.
The concept, okay. So the just like I mentioned before, so it is a property of the electron. Okay. Now it is just like charge. So if you say what is charge, we call it charge, and the definition is no, okay. So the manifestation is that if you have two similarly charged things, they repel. If they are oppositely charged, they attract, and we just call it as charge. Okay. So if you say electron has charge, if you say an object has charge, then you say it is a excess or deficiency of electrons. But what about an electronic charge? It's the same problem. It's a property of the system. It's the same as spin. So spin is a property of the electron. Its manifestation is that it behaves like an angular momentum. I don't know how else to put it. It's like mass, charge, spin. It's intrinsic to the system. You don't. There is no mechanism which generates it. Okay, and this property, it is a relativistic property. So unless you consider the electron to undergo relativistic motion, you would not be able to get spin. When it's a non-relativistic picture, because we want the electron to show the effects of spin, we augment these equations with the spin of the particle. But it only arises naturally when you allow the electron to move relativistically. Perhaps later.
Actually, ma'am, actually I could not get the physical picture behind the spin. I mean, if we consider two charges, like you explained, if they are of the same charge, they repel each other. Similarly, I cannot get the physical picture behind the spin. How can we imagine it?
The picture behind the spin would be if you consider its interaction with the magnetic field. That is the easiest to understand. So if you see if there are electrons and you allow them to interact with the magnetic field, you will see clearly that there are two types. One would move into a magnetic field and the other would move out. So similar to being attracted and being repelled. And you would see there are two types. So then you say that there are a free electron can have two types of spins, up and down.
Thank you, ma'am.
Yeah. Okay. Fine. So we're nearing the end of the class. So I will quickly go through the last few developments. Okay. So then after the relativistic electron, then simultaneously there was the development of quantum chemistry. So bonding was being started to be explained by Schrodinger's equations, and the molecular orbital theory came from Hund and Mulliken in 1927. Then Wigner also started relating symmetry to degeneracies of quantum states, and in bits and pieces, slowly, quantum chemistry developed. Then in 1946 to 48, Rabbi, Lamb, and Kush, they discovered the lamp shift, which is that the 2s and 2p electrons of energy levels of the hydrogen atom, they are not where we should. Okay, and then this threw into question even the relativistic quantum chemistry, and then Feynman came up with his quantum electrodynamics. So he first formulated the path integral formulation in 1948, and then also quantum electrodynamics. And this then explained the lamp shift and the discrepancies of Dirac's theory. Okay, so there is already the levels of the quantum theory is going deeper and deeper and deeper. Okay, yeah, and then okay, and we will finish now with the last few. So what a very spooky phenomena. So in 1949, Ehrenberg and Seide observed that even when there was an electron in a region where there is no magnetic field, then it was affected by the magnetic field which was present outside it. So if there was a magnetic field outside a region in which an electron was confined, it could still feel it. So this was a very weird effect. Sorry, I mean Ehrenberg and Seide did not observe it. Sorry, they suggested that this would happen. Okay, this was a theory. They suggested that this maybe we can observe this. Yeah, and then in 1959, Aronov and they also proposed the same thing. Okay, and then
I know that. I'm saying even in Amazon I checked.
Chambers did the experiment. Okay, then hello, and this was called the Aronov.
Okay. How?
Okay.
तुम जो खरीदा था K360 तुम जो खरीदा था अभी ये दोनों में क्या फर्क है आयन से दोनों?
So I think yeah, students. So I think we will stop here since it's 5 o'clock today. We will go for the next 50 to 70 years till date.